Let's do now this application about the circular motion. Application 121. The Earth describes around the Sun with uniform motion and orbit assimilated to a circle of radius r equal 1.5 times 10 power 8 kilometers and t equals 365 days. So we have, in this exercise, we are considering the Copernican reference frame where the Sun is considered as the center of the solar system and the Earth describes a circle around the Sun. So in this exercise, we are told that the Earth is making a uniform motion, a uniform circular motion, and the circle, the radius of this circle is given as r equal 1.5 times 10 to the power of 8 kilometers, and we know the period of rotation of the Earth around the Sun. It's equal to 365 days, so it's 1 year. Question 1. Determine, with respect to the Copernican reference frame, the translational velocity of the Earth's center as well as its acceleration. So we want to find the translational velocity of the Earth's center. We need to find the velocity vector of the center of the Earth and the acceleration. So we need to use the circular motion. We need to use the formula V equal omega cross r. So omega is the angular speed, r is the radius of the circle. It's the distance from the Sun to the Earth. We know that V is along tau, so tau is the unit vector tangential to the path. V vector is equal to the magnitude of V times the unit vector tau. Now to find the magnitude of V, V is equal to omega times r times sine of the angle between omega and r. So where is omega? Since the Earth is making a rotation around the Sun, so it's rotating in this direction, then the right-hand rule will tell us that omega will be a vector perpendicular to the screen, and this vector is directing toward us. It's pointing to us. So we can see that the angle between omega and r is equal to 90 degrees. So the magnitude of V is equal to omega times r times sine of the angle between omega and r. So times sine of 90. Therefore, V is equal to omega times r. So we can write it as 2 equal to 2 pi over t times r, because omega is equal to 2 pi over t, where t is the period of rotation. By replacing each term with its value, we'll obtain V equal to 29.88 kilometers per second. Here, pay attention to the units. You can convert it to this value to meters, and then the value of the V will be in meter per second. Okay, now we need to find the acceleration. So the acceleration is equal to at plus an, but since at is equal to 0, because we have a constant velocity, so at is equal to dv over dt is equal to 0. So the acceleration is equal to the normal acceleration. It's given by v2 over r. And we can deduce the value of the normal acceleration. So the magnitude of the acceleration vector is equal to an. Okay, now in question B, calculate the velocity and acceleration due to the rotation of the Earth on itself. Now we are considering the rotation of the Earth around itself. We need to find the velocity and acceleration for 2 points. For a point on its surface, for a point M here, on the surface, located at the equator, and for a point at a latitude of 40 degrees, and this is point A. So point A is this one. The radius of Earth is taken in this exercise as 6,400 kilometers. Okay, we need then to find VM, AM, and VA, AA. So we need to apply the rule, but pay attention to the direction of the vectors. So again, we will use A equal omega squared times R, which is the same as V2 over R. And this is equal to 2 pi over the period of rotation now, the period of rotation around the Earth. Okay, please note that T prime in part B is different than T in part A, because in part B we are considering the rotation around the rotation of the Earth around itself, whereas in part A we are considering the rotation of Earth around the Sun. So T in part A is different than T prime in part B. So for the acceleration, it's equal to 2 pi over T prime squared times R. What is R? Which radius is to be considered here for R? This small r is the radius of the circle described by the point while it's rotating around the axis of rotation. So this is our axis of rotation, and we need to draw this circle. So point A, for example, is making this circle. In this case, the circle of the radius is equal to the distance from this point to A. Okay, so if we consider this point A, and now small r is equal to capital R sine alpha, because sine alpha is equal to the opposite side, small r, over capital R. Therefore, small r is equal to capital R sine alpha. Okay, and alpha can change depending on the point, depending on the location of the point. So T prime here is 1 day, it's 24 hours. So to find the velocity vector, we write the definition of the velocity vector. In the case of a circular motion, it's omega cross r, and it's equal to the magnitude of v along the tangential unit vector tau. Now, if we take the point M, let's take the point M first. So for the point M, alpha, which is the angle between the axis of rotation and the vector starting from the origin of the Earth toward our point. So in this case, alpha will be equal to 90 degrees. So we are considering now point M. V is equal to omega times r times sine of the angle alpha, where alpha is equal to 90 degrees. Omega is equal to 2 pi over T prime. So you will find V equal 465.4 meter per second, and the acceleration, you will find it as 3.4 times 10 to the power of minus 2 meter per second squared. Now for point A, where alpha is equal to 90 minus 40 degrees, they said that we have an angle of 40 degrees. It corresponds to the latitude. So here is the angle 40 degrees. This means that alpha is equal to 90 minus 40. So alpha is equal to 50 degrees. And we can find V. V, it's equal to omega, again, times r times sine of alpha, where alpha is here equal to 50 degrees. And then we can get V, it's equal to 356.5 meter per second. And we can also find the acceleration A. It will be equal to 2.6 times 10 to the power of minus 2 meter per second squared.